I'm Adam Russell with SymbiosisTX.com. Today we are working on remineralizing this land. We're working on a basin, basically a C-shaped basin with two drainages that come in from the north and the west side. So we put leaky weirs in, which is basically a dam, a rocky dam feature, water slowing feature, and now we're to the point of mineralization. So we stopped and slowed the water coming out of the drainage. We're currently building swales and berms on the rest of the drainage. We put out 25 tons of basalt dust from the Canipa, Texas basalt mine. We used screenings, which is basically their dust. It's $10 per ton, which is extremely cheap, given that the world is pretty expensive these days. This is all of our very specific minerals. In order to get to here, we first come through here and we take a soil test. So any soil test is going to be a conglomeration of multiple samples. So in order to send off one soil test, we took 5 separate test holes, took a 1 inch by 1 inch by 6 inch tall rectangular column of soil, put that in a plastic bag, and did that 5 different times. Mix it up, package it, send it to Logan Labs, requesting the complete test with extras, plus recommendations from Bill McKibben. What that gives us back in an email is the complete test results, which is everything that's dissolved out of that dry soil with a strong acid, basically a 3.5-ish acid, which dissolves everything out of there. So we get a bunch of numbers of a bunch of different chemistry that's in there: calcium, magnesium, potassium, boron, silica, manganese, magnesium. I think I already said that, but basically everything that's in the pantry. We also get a paste test, which is that dry soil mixed with water. And so we get more of what's water soluble. And so somewhere between that extreme acid and the water, somewhere between there is what plants can actually bioavailably pull up with their roots and actually dissolve with their enzymes and the different fungal relationships and bacterial colonies that are changing pHs and chemistry in the soils. So we get the complete test and the paste test, and from those two, Bill McKibben gives us recommendations. Those recommendations come in pounds per 1,000 square feet. So in order to get per acre, we take, let's say if it's 5 pounds per 1,000 square feet, we multiply that 5 pounds by 40, and that's how many pounds we should put per acre. Here we have 2 acres, so then we have to multiply that by 2. So the math and conversion of soil tests can be pretty daunting, but just take your time, write it all out, have somebody else sit next to you, write it all out, compare notes. It's a lot of acres to square footage to pounds to then tons, and then sourcing everything from where it comes from. This material is 90% elemental sulfur. We have a very alkaline limestone soil here. So sulfur is that first chain link of events that allows things to start to dissolve and become available, increases surface area between everything else. Then we have boron in Hugh Lovell's Biochemical Sequence, which you can look up on Google. Sulfur is the first step, boron's the next, because it increases sap pressure, and boron drives calcium. So you may have lots of calcium like we have here, but it's immobile because you don't have any boron. So boron's the next step. We don't need much boron here. For 2 acres, we only need about 23 pounds of fertibor. Fertibor is 15% boron, solubor is 20% boron, and borax is 10% boron. So depending on what source you're getting it from, in let's say 10 pounds of borax that you could get off the shelf at the store, usually used for laundry detergent, there's only 1 pound of actual boron. Whereas if you got a bag of solubor, which is 20% boron, in 10 pounds of that material, there's going to be 2 pounds of actual boron, which you're trying to get. So the percentages of how much is actually in the 50-pound bag is very important so that you don't just dump 50 pounds of borax and assume you got 50 pounds of boron. It's a little bit more complicated than that. But right here we have sulfur, starts the biochemical sequence. Boron, which increases sap pressure in plants, allows those nutrients to get up to the top of the plants to actually be utilized in photosynthesis. The next is silica. Our silica source came from the basalt dust that we put out. That basalt dust has everything that a volcano has erupted in the form of magma, and it's very high in silica. So that's the silica is providing the rebar and allowing the plants to grow big and tall and strong now that they have sap pressure from the boron to get it up there. And then it moves further down the biochemical sequence into, I believe the next is calcium. And again, boron drives calcium, so you can have all the calcium in the world, but if you don't have boron, then it's not going to be able to be usable. So in this pile right here, we have 500 pounds of 90% elemental sulfur, 400 pounds of phosphorus, pelletized in molasses, 500 pounds of K-mag, which is a combination of sulfur, potassium, and magnesium. It's a deposit that comes out of Utah. 40 pounds of manganese sulfate, 23 pounds of boron, 80 pounds of zinc sulfate, 16 pounds of copper sulfate, 200 pounds of ammonia sulfate. Any materials that we're using, if it's not an animal-based product, ideally we would use things like bone meal, feather meal, poultry manure, all animal-based, a little bit more bioavailable. But if you're gonna go a different route of bags of minerals, then we want the sulfate form. Chloride forms of minerals can cause problems. Just like sodium chloride is table salt. If you consume table salt, a lot of table salt, you get osmotic pressure changes and swelling in your appendages. It causes higher blood pressure. That chloride is a specific salt that just shifts water a lot, and it can collapse clays as well. So there is a product called potassium chloride, which has been used in the conventional agriculture for a long time. But what's interesting about that is if you soil test and you're deficient in potassium and you put on potassium chloride and then soil test immediately afterwards, it's very likely that your potassium has gone down because that chloride pulls potassium out of the clay structure and it collapses all of the clay that's in that area. So like everything, it's very complicated. So long story short, we don't use chlorides, we use sulfates because the land's going to use the sulfur and the sulfate anyways. And then the last thing is gypsum. Gypsum is a cheap source of calcium and sulfur. It's just a pretty good amendment. If you're low in sulfur and a little bit of extra calcium on an already high calcium soil is not going to be the end of the world, because in the biochemical sequence you have sulfur, boron, silica, and then calcium. So even if you have a sea of calcium like we do in this limestone soil, it might be all locked up and bottlenecked and immovable. So a little bit of extra calcium that's in the gypsum is going to help everything just continue to move. So our process today is we dumped all the bags on the top here. We shoveled them on top of each other to mix them downhill. First, to choose this location, we made sure that the wind was blowing this way. With all these elemental salts, they're very aggressive. They want to bind to things, specifically things that involve water membranes, like your lungs, your eyes, your mouth. So anytime you're working with it, stirring it, downhill from it, we need a respirator, we need full goggles, gloves. The better option of this, after doing this a few times, instead of putting it in a cone seeder and having to really manage which direction the wind is blowing or not blowing, is send all of this to a compost soil yard that has the big machines with the AC driven cabs. Let them mix it all into compost, and then on site you just get a delivery of compost. Obviously there are different costs, and you're not going to be able to put that compost out with a cone seeder. You're going to need a manure spreader. So the machinery changes, but ideal world, for me personally, I would use that method every time. Why we're doing it this way is because time, availability, cost, all of that goes up when you send it to the soil yard. They mix it, you have to bring in compost. And for this particular project, we didn't have access to a manure spreader. So those are my thoughts on remineralizing soils. We got all the volcanic basalt out. That's going to increase the not only the minerals that are in basalt. If you think about volcanic island chains, it's all basalt and magma and lava, all volcanic. So not only the salts and minerals in there, but also there's a quality called paramagnetism that is basically a very subtle form of magnetism that just generally nudges plants up. It's a force that just nudges them away from the ground. And so it's one of the reasons why you see things growing so fertile in places like Hawaii. Not only is it on the equator, which obviously helps, but getting basalt dust into systems is generally going to help. So we're going to put it in the cone seeder. We're going to make sure that the wind doesn't change, and we're just going to put all of this on contour as high on the property as possible. And then we'll allow the rain to settle it down into the lower valley. If we can, we're going to put a stripe on contour at the high point, and then a stripe on contour in the midpoint, and then just let the rain kind of mix and blend everything else. We'll take the skid steer, scoop it up, and load the cone seeder, and that's how we're getting this material out. Go ahead and get a food forest, perennials, pollinators, and regenerate this whole lower valley for this couple who eventually is going to want rotational grazing and a potential biodynamic vineyard right around the corner.